Number of ways to look at it. For metals, you can see these leaves all around, how smooth it is. It really doesn't have any roughness to it. And what happens is as the crack continues from one cycle to the other, it just opens and closes and go very slowly without pulling and stretching the material a whole lot. So that's why you don't have much roughness to that fracture. So it's one of the basic rules to at least throw the hypothesis, well, maybe this didn't fail all at once. Maybe this is not an overload fracture. So we're going to cover in more details what I call the slow cracking or the pre-cracking. It can be creep, fatigue, environmental cracking, something that happens slowly, reaches the length, and then you have the overload. That's tomorrow. Today, we're going to focus more on the difference between a tensile test and when you fail a piece of metal, and really it looks like you broke a piece of ceramic, because we have that happening quite a bit. Tool steels are notorious for that. You can have just an Allen key that's going to snap on you, and sometimes it will snap if you have the size marker. I've seen that in some failure analysis. You have the size marker, it's a 1/4 inch on the, if you get a little Allen key like this. So right here, if they put a size marker here where you have the highest load, crack starts right there, because you have stress concentration, and it's essentially a brittle material even though it's steel at ambient temperature. So we want to tie in what makes the difference. Why is this one brittle as opposed to being very ductile? That's the goal of today's class. And the best way that I thought about to introduce it is we have two main processes. We have Monmesis, which is plasticity. And we've talked about it when we were in deformation processing. I talked about dislocation, they multiply, eventually you reach a certain flow stress. At any point in times, you have the flow stress. If you're talking about a material in service, normally you use the yield here. So the criteria, it's going to flow if the stress of the capacity of the material to resist flow. So I'll put in parenthesis here, sigma yield. Just, it's a material property. So on this side we have the material, and this side we have the loading. It's always important to keep that in mind. What am I looking at? It's the same thing in high school. You learn that you want to put units when you run a calculation. In material science, am I looking at the capacity or the load applied? So if my material capacity is exceeded, so I'll put it the other way, then I get flow. Or the other way, you just really have to think about which way you want to look at it. And then it's really a deviatoric stress, if you remember. So I can write it any way I want here, as long as I make differences between the three principal stresses. So I'm putting numbers in Roman format here because this is all, I'm missing 1 and 2. This is all in the principal stress system. So I'm essentially taking the most complex stress state that you can think of, looking at it in the principal axis, so there's no shear in that axis. I'm making this difference so that I'm comparing essentially the whole capacity with my material capacity, my loading with the capacity. So whether I have flow or not, this is one thing that's happening with the material. Whether we're going to break, that's the Griffin criteria here. So I can essentially say if my stress is greater, so I'm putting it, which way should I do this one? To be consistent, let's do it the other way. I'm applying a stress, and I want this condition where my material capacity is less to say it's going to break. It's going to break under these conditions. I have the surface energy, I have the crack length, and other stuff here. I want to make sure. What pi, it doesn't matter. This is a material characteristic. When we talk about a brittle behavior, and that's Griffith. When we talk about a material behavior that's brittle, we worry about how big the crack is. You could say the crack is not something that's intrinsic to the material. It's not so true when we talk about ceramics. Ceramics have a lot of porosity. It turns out that these porosity normally are where the crack will start. Castings will have a lot of defects as well and anomalies on the surface. And a lot of times if a casting fails without ductility, it will be related to how strong the bond is in terms of surface energy and what is the maximum defect size I have on my casting. So brittle and ductile, there's really not a whole lot of relationship between them. One really has to do with how much load I'm going to put on. I mean, if I keep adding up here, I can have a very, very small defect and it's still going to break. In this situation, if I'm just applying a pressure, even a triaxial tension, I won't yield. I mean, the whole material will start forming voids inside of it, but according to this rule, nothing happens in terms of plasticity. Plasticity is driven by shear, and a fracture itself is driven primarily by tension. So when I put the sigma here, I just say it's a tension. So whenever we look at any specific application, if we talk about steel and going from a ductile to a brittle transition, lots of times you can have an effect of the environment, the temperature, or the processing condition on this flow stress. And you can also have an effect on these characteristics here. With respect to temperature, I do want to really point out that this is going to vary the most because it requires the movement of dislocations. And the movement of dislocation is thermally activated. So it means at high temperature, I have creep. The dislocations just keep going back and forth. They will recover themselves. You can have recrystallization. You have all sorts of things going on. At ambient temperature, well, it will harden. So you're going to multiply the dislocation. At colder temperature, you don't completely stop the deformation. If you were able to deform the material in compression even at cold temperature, this still works. You still have flow of material, but it requires more stress. The value here of the flow stress is going way up as you decrease the temperature. And that's, to me, the best way for you in hopefully 5-10 years, maybe 20, to remember this, even if you don't work in the area of material properties. So I'm putting here the temperature, and here we're going to have this expression. So the stress that it takes, so this is definitely a stress, but the stress that it takes to fracture with a given defect size, it's going to have some effect of temperature, so I'm going to just sketch it out this way. It probably even may stabilize here a little bit. So now with steel, what happens with the other equation here for the flow stress, this expression, you get to very high temperature where it's almost the same, and then eventually goes way up and crosses over the other curve. Aluminum is a slightly different animal. Most of the time, aluminum is lower strength to begin with, but it's also not going to vary as much as you lower the temperature. So what happens to steel right here is, well, steel is BCC, so I'm going to put it right here. And aluminum is FCC. You have fewer planes to complete the deformation. You also, in the BCC structure, you cannot have what we call partial dislocations. It's all real dislocations. So there's a point where the screw dislocations, because you need both, and we haven't gone through all those details, but you have the screw dislocation and the edge dislocations, and it gets to a point where only one of them you can really move. Well, that makes it very hard to deform. And that's why the stress, the flow stress, is going way up at a certain point. It will be influenced by some impurities in the steel. And that's the reason for that is you're talking about moving the dislocation. So if you have small impurities that will pin down a little bit those pore screw dislocation and stuff on top of everything else that we have, it's moving that curve one way or the other. It's essentially going to make it more brittle because it's going to increase the flow stress. So I'm going to say with impurities here. So the aluminum, again, has more deformation slip systems and has partial dislocation, so it's not as sensitive to temperature. The energy to have one step moving is less. Therefore, the thermal activation is less, and you have less an effect of temperature. But for all these cases, the other curve, with respect to the size, doesn't change that much. You're really talking about what is the energy when you have an open crack as opposed to a closed crack. It's related to the strength of the bonds, and there is some variation of temperature with that. But it's really it's more on the plastic deformation side of the equation that you're going to have a variation. So when you say I don't want a fracture, you have to work both ways, relatively independently. And I'm giving the example of temperature, but we should also talk about the effect of heat treatment on the alloy. There's some high-strength steels that are notch sensitive. A lot of aluminum castings are notch sensitive because you can increase this by having a very fine casting structure or by making martensite, but you're not going to increase this one. It's the same way. So trying to work the Griffith equation with metals is pretty difficult. We probably going to talk a little bit about stress intensity. I don't want to go too deep in that. I don't want lose track of the big picture here. But essentially, you have one side that's really about, do I want to open up the material? And you have the other side that says, do I want to deform? The examples of that that we can talk about the most is the difference between a tensile specimen and when you do these impact tests. So the tensile specimen, we talked about quite a bit. You form this cone and cup structure. And this was something that some of you were a little surprised about the cracking starting in the middle. And the reason that I mentioned was that's where you have the highest stresses here for opening up because everything becomes concentrated. In reality, we have a lot of materials that fail without the necking. It's just almost like a cut. going through right through the material. When we look at it after the fact, this is something we'll see sometimes where there are multiple zones on the fracture, and you have it in the one I circulated earlier. So this one example here, the reason I put these arrows is really related to the crack propagation line. It's because between that I had this little ridge. The ridges, most of the time, just separate two cracks that were not exactly on the same plane. So they show you the step to go from one crack to the other. And most of the time, the overall crack propagation direction is parallel to these crack propagation lines. Now, this example we have here is the crack stop. And that's where you see the little dotted line, or change the way it's deforming. So these we call the crack arrest line, and they run perpendicular. We only have them here in the middle in the example that I circulated. So when all the cracks got up together close to the middle, there's this one zone left, and then at one point in time, this is what the amount of material that was still connecting was right here, and you can see the crack arrest line around it. It's a little button. So these little, it may look like little details, but they make a big difference when it comes to looking on the surface and making some basic interpretation. These are the only two types of line that you really have to worry about just by looking visually. So just with that and a flashlight or maybe a little microscope that goes to 3 to 5x, you can tell a lot about what happened. I have a more complicated one here that I'm going to circulate. That is with respect to crack propagation line. I'll draw it right here. So I'm almost giving you the answer here, but that's fine because we don't have the time. It's not a fracture class. And the overload is here. There you go. So it's another example. There were three main initiating cracks. Over here, it's easier. We just have one origin, and it just keeps going to the other side, and there was bending load. The example I'm giving you there is more of a tension because the crack started at a different location around and went to the center. Yes? So you work backward to determine the origin. That was the question. You have to look at the two types of lines. You have the crack arrest lines and you have the crack propagation line, and they will point you to one origin or multiple origins. So in this example, if we look at these crack propagation lines right here, they all point in this direction. So that's where it started. Even if I didn't know this and I'm looking at this, I know it didn't start this way because it was spreading away from that area. So you have to look at the spreading, essentially. And because we're looking at a macroscopic level here, it's fairly straightforward to say that from the initiation area, the crack propagation line will diverge. There are other lines on the fracture surface that will converge, but we'll treat that separately. The other thing that you have to be worried about is when you have an arrest, after that you generate new lines, so you have to be careful with that. But the easiest for me is to look at this line right here. It's spreading out a little bit, so I know it didn't start this way. I look the other way, it's diverging as well, so I know I'm right in the middle. That's pretty much an experience, but at the same time, when you think of it, there's really no way that I could pretend like it started here, and then, you know, how would I make this going the other way, knowing that these are steps. So it is really, you know, we know the material is only going to do to minimize its energy. So the reason why you have multiple cracks is there's some variations in the material, and then also the crack wants to go here and the other doesn't care. It wants to continue its own way, and then you have a little extra energy to make that line, that crack propagation line between them. But it's less energy than to say we all going together. That's another example. I think based on what I just said, you could take, this is about 8 inches in diameter. It was a propeller for a big boat, speedboat that only half of the prop is in the water. So if I'm looking back here, this is coming out of the hole. It's a straight shaft, and only half of it is in the water. So meaning each time I turn, I have a lot of bending moment in that shaft. And looking at it after the fact, I see all these crack arrest line. They all sort of come back to these corner here. So if I'm looking at this in more details, that's where I see the crack propagation line here. They all radiate from this little area. It was a gouge on the surface. That's where the crack started. And the significance of that in this particular case is if there were gouges all around the axle, I'll have initiation sites everywhere. Because I have just there, the load was the same because you keep going all around. I mean, there may be a little effect of where exactly the blade is on the prop, but overall, as you turn, you always had a bending moment and a torque. But the torque, normally, the torque can matter. In this case, it really didn't, because this was perfectly transverse through the material. And it's a large section at 7 inches. Yeah, it's a powerful engine, I'm sure, but it was really a bending situation. And this crack propagation line allows you to narrow down exactly where it started. And you can also infer something else. If you start from here, definitely up to here, you had a 7-inch axle that had a crack halfway through, and it was still holding on. So it wasn't what I call an overload case, because with 1/2 of the section and all the stress intensity, everything that's associated with having a crack in the material, you were still holding on and operating. It's a little vicious because unless you inspect, everything goes well until you reach the fracture toughness of the material and you had a fracture. So somewhere around here, and it's hard, I think it's here, but it could be a little further. So here or beyond, at one point, you exceeded the capacity and reached the condition of final fracture. It happened in our piston example when we only had this much left. So we had less load here than over there, but this is still a low load condition. And I brought in class these long bolts the other day. These were retaining piles in a canal, and it's the same thing. They were broke about 35% of the surface area before it failed. So somebody else told me, well, this is really an overload. There was too much soil pressure. So I just told him, well, so how did you measure the soil pressure? He said, well, I didn't measure it. Okay. And then I said, well, I measured the load from the fracture surface, so we have a problem here. I think my strain gauge is better than yours. So it's something to keep in mind that there's just a lot of information to get out of a fracture surface, and it's always fun. It's fun when a lot of people have already looked at it, but never really appreciated that there was a pre-crack. It makes the difference in terms of the information that you have. So from the schematic, what I said was the overload is right over here, this little corner. Everything else was slow cracking. All right. So we all know about impact testing, either for plastics or metals. For metals, the most common way is this Sharpie V-notch. You can do it normally with these two supports here. So you take a bar of your material. The orientation does matter. If you're looking at a pressure vessel that's thick, maybe you want to see if the crack is going to be a laminar type of crack as opposed to a transverse crack. So the way you cut that bar makes a difference. And you're just looking at the energy loss to go and get the pendulum across. So when you get the pendulum across, there are situations where you won't break the sample. The sample is just really going to stretch and open up a crack, but without a complete separation. That's if you have a lot of ductility, or you'll just break it in two pieces. The ISOD type of test here, where you drop the weight, is more common for plastics. And it's the same with plastic. Normally, because the ISOD was originally set up for metals, you can break the plastic most of the time here, even if it's a very high strain composite, because you get so much capacity and depending on how you control the load here. But it's giving you a combined response. It's only as good as what you're testing. So you're testing the material under a condition where you have a notch. It's not a crack, it's a notch. And then you're loading it rapidly in all those cases. So that's what we call the impact test. What you find normally, and we have a bunch of materials here, and this schematic, you can forget about the dislocation plot here, but we're looking at the energy it takes with respect to temperature to break. You see a lot more variation with steel than aluminum. So what happens with the steel at low temperature is this more controlling effect where you really start having some of this brittle behavior going on. And that is where also you taper off. So if I look at the steel curve, this is kind of a regular structural steel. It's very high, it goes down, and then eventually it's going to become less temperature dependent again because we're only dealing with the brittle behavior side of the equation. That's why we have this inflection point there. So it's always good to think about, so what happens next? If I'm going to be in this brittle zone and go to the very high ductile zone, what happens to my material? So this is a case of very high strength. So the bar was rectangular and straight at the beginning. So I start with my rectangular bar. I have my notch in it. It's all straight. And then it bent, in this case, somewhere around 60 degrees without completely separating. That's the extreme case. What happens in this situation is this top side is going to become narrower because it's stretching, and this is going to expand. So when you look at it on a top view here, this is what happens. So it's reducing in width here. That's the high temperature case. We're starting from the right side here. And then the compression side here is wider. As you reduce the temperature, it becomes squarer and squarer until it's really just a cut through the material. What we do with these Sharpie tests of steel is we end up making an evaluation as to whether it's a ductile tear fracture. So in this case here, they say it's 90% ductile. There's still a little area in the middle that is more of a brittle separation behavior. And as you reduce the temperature, you're going towards just a brittle behavior. So that's the Sharpie test. It has a lot of limitations in terms of being able to use that exact data for design. I mean, if I run this test, it won't tell me exactly, well, you know, at what temperature can I still use steel. It depends on how much impact load you expect. It depends on whether you're going to have stress risers or not, if you're going to have notches in your application. But it's a good way to compare materials. So historically, what happened is they had failures on large ships, on bridges, and then they went back and say, okay, now we need to, you know, get a steel that's going to resist these conditions better. And they arrived to that test to rank material one with respect to the other and be able to have structural steel that's capable of withholding cold weather. We're not cryogenic in most cases. If you really have a very low temperature application, you have to use austenitic stainless steel, so 304, 316, which is an FCC structure, so it doesn't have this increase in flow stress as you lower the temperature, or aluminum, for example. Now we talk about steel having this behavior, but titanium can have this behavior too. There are other materials that you have to worry about the effect of temperature. Tin came in because we were working on a solder joint, and around the minus 100 degrees centigrade is where tin will, you essentially start having the this curve starting to peak right up, and you have more of a reduction in ductility, and you have a very brittle behavior. Moving backward a little bit before we get there, I mentioned about high-strength steel. So the way you make tool steels, that's just a very limited example, but you make tool steel most of the time by keeping your heat treatment to the end. So you work the steel, you machine it, and when you're done to the shape, you do the final heat treatment that gives you the high hardness. But from that high hardness, you're working on the ductile behavior curve here, and you become sensitive to notches. So impact wrenches, and also there are a lot of applications where you have to make sure that you don't go to that brittle behavior even if it's at ambient temperature. Cast iron, and we could talk about, you had a question?
Yeah, can you talk about that trend down, like the previous slide, because I noticed that as this slide here, as the hardness is increasing.
The ductile behavior is not as high energy, right? That's what you're interested in. So if we look here at a high temperature situation, the lower strength steel will give you the higher energy. And what happens there is because you have a lower yield strength, you're going to be able to deform more before you reach the fracture condition. It gives you more distance. If I'm going backward here, and that's a very, very good question. So if I go back here, my energy to fail, I would argue with you that it's the time of taking this curve all the way to the next one by strain hardening. If I make that curve lower, I'm going to consume a lot more energy before I reach the fracture condition. So every heat treatment, most heat treatments that we do on material will affect this curve. So if I start with a regular structural steel, I'm say right here, very low strength for a given temperature, but I'm going to be able to displace and flow the material a lot before the stress level, the flow stress, becomes high enough to break. If I have all the heat treatments, it's a tempered high strength steel, this curve is still the same, but you're starting at a higher point. That was a very good question, and right on time too. Thank you. Any other questions? So what I was going to finish with is just showing you a little bit what happens under the microscope. So if you take any piece, including the two that I circulated, and you go at high magnification enough, you're going to be able to say, how did the breaking happen? So we're more interested now about this curve here when we're really reaching the capacity. If we are at low temperature, we can have cleavage. And that's what I'm showing here in this image. And because of my accent, I'll write it down without making any jokes here. So what happens in cleavage is you separate between the inside the crystal, you separate between atomic planes. So you try to find these atomic planes that are further apart and have less energy to make this happen. So there's going to be a few orientation in the crystal orientation that'll be more favorable to opening up like this. And because most metals have a lot of crystals, many grains in them, when you go from one grain to the other, that orientation is changing. And that's why you see all these lines here. And these, you could call them also crack propagation line, but they don't. That's the one example, and this is looking at high magnification under the microscope. It's one example where the lines are spread out and they come together. So they converge instead of diverting. And the idea there is to reduce the number of steps, because each step between different planes here consumes a lot of energy. You need flow of the material there. It takes a lot of energy. So if you cluster them together, you're reducing your overall energy it takes to fracture. Don't get too worried about it. It doesn't happen very often. But there's another class I teach on fracture fatigue where it's a good exam question because it's the opposite of what most is happening. So you can